Hello, welcome to a new video on properties of group isomorphism. In the property that we are going to discuss in this video states that if phi is an isomorphism from G on to G cap, then phi inverse is an isomorphism from G cap onto G. Let's discuss the proof. Since it is given that phi is an isomorphism from G onto G cap, it is 1 1 and 1 2. So if we define phi inverse from G cap to G such that phi inverse of phi A equal to A, phi inverse of phi of A equal to A whenever A is mapped to phi A, then we can now see that since phi is 1 to 1 and 1 to, phi inverse must also be 1 to 1 and 1 to. Now it remains to show that phi inverse preserves the operation. See, that's the third property for proving that a given function from a group to another group is an isomorphism. So we want to show that phi inverse preserves operation. So let x and y be elements of be two elements of G cap. Let x and y be two elements of G cap. Then there exists uh, two elements a and b in G such that phi a equal to x and phi b equal to y. See, exactly there will be two elements in G because the operation or the function phi is or the isomorphism phi is 1 to 1 and 1 to. So there exists two elements a and b in G such that phi a equal to x and phi b equal to y. Therefore, phi inverse of x directly we can define phi inverse of x equal to a and phi inverse of y equal to b, and then phi inverse of x star cap y. What is what is this value? So phi inverse of we consider phi inverse of x star cap y. It's equal to phi inverse of x, since x equal to phi a. So phi inverse of x equal to phi a, then star cap of phi b. Okay, phi inverse of phi a star cap phi b, that equal to phi inverse of we can write that it's equal to phi of, you can combine this and write that phi of a star b here inside the bracket, and this expression can be combined. So phi of a star b, and this star is the operation in the first group, a and b are the elements of the first group. So phi of a star b, and then we take phi inverse of phi of ab, and phi inverse of phi, again that cancels each other, and we get that a star b, and but a star b equal to phi inverse x and phi inverse y respectively, phi inverse y respectively. Okay, therefore they are substituted, and then thus we get that phi inverse of x star cap y equal to phi inverse of x star phi inverse of y. See, phi inverse of x star phi inverse of y. Here we use only one only star operation, because this operation it's happening in the first group, and this is the end of the proof. Okay. Now, next property states that if K is a subgroup of C, if we consider a subgroup K of a group G, if K is a subgroup of G, then phi K is such that phi of a small k, phi of K is defined as phi of small k is that where K is an element of K is a subgroup of G cap. We can use the method to prove that a subset of a group is a subgroup. So that method can be two or three methods there, and one of the method can be used to prove this. So for that, let x and y be two elements of phi k. Let x and y be two elements of phi k. If we can show that, see, if we can show that x star y inverse is an element of phi k. If we can show that, so whenever x and y are elements of phi k, if we can show that x star phi inverse or xy inverse is an element of phi k, then we are done. Therefore, then there exists, see, in this situation there exists a and b are elements of k. There exists a and b are elements of k such that okay, there exists a and b when this happens when x and y are elements of phi k. See, if x and y are elements of phi k, then there must exist two elements a and b in k such that x equal to phi of a, and y equal to phi of b. Right. And since k is a subgroup of G, since k is a subgroup of G, you know that a star b inverse is an element of k. It must be an element of k. A star b inverse must be an element of k. And so phi of when we apply phi on this element, then phi of a star b inverse, phi of a star b inverse equal to phi a, phi a, then star cap phi of a star b inverse is equal to phi a star cap phi of b inverse, phi b inverse. It's an element of it can be written as phi a. It can be split as phi a star cap phi of phi b in phi of b inverse, and that equal to phi of phi b the whole inverse. Okay, it's an element of phi k. Now it remains to show that okay. It now remains to show that phi of b inverse equal to y inverse. We want to show that phi of b inverse is equal to phi of b inverse is this element. This element is equal to y inverse. For that we consider phi of b star b inverse. Phi of b star b inverse splits into, but here we get identity element e. So equal to phi of e, equal to phi of e equal to e cap, and that equal to phi b star cap phi b inverse. So this is equal to phi b star cap phi of b inverse, and therefore since phi b equal to y, so that equal to phi b since phi b equal to y star cap of phi of b inverse, it's equal to e cap, and therefore see by now it means that, what does it mean here? When we see this expression, we can say that phi y into the element y star cap phi b inverse is equal to e cap. That means that inverse of y is this element. This is the second element, is the inverse of y. So y inverse is equal to phi of b inverse. Okay. So and then going back to, thus we get that phi y inverse is equal to phi of b inverse. Okay. Going back to the expression 1, and we can show that phi a phi a star cap phi b inverse, phi b inverse is equal to x star cap y inverse. So okay, then substituting in 1 in expression 1, where is it? And this is one expression 1, and this expression 1 says that phi of a star b inverse is equal to phi a star cap phi b inverse. And here phi a equal to y, we can substitute phi a equal to phi a equal to x. Phi a equal to x you can substitute, and phi b inverse equal to y inverse, that can be substituted. These two element numbers can elements can be substituted. The x then we get that x star cap y inverse is an element of phi k. So phi k is a subgroup of G. Okay, that's the end of the discussion of the properties. Okay, thank you.